I want to talk a little bit about the big question, the hard question especially, is which one, who's got the delta T naught, the proper time in this. So I wanted to look up last night and see if there's a better way I can explain it, and I've come up with two new things, one of them directly from your reading, that I think will help. So, if you flip back to that page right after we did the derivation, and it's got the definitions of the delta T naught, delta T and stuff, I've got a tiny bit to add to that. Let's see, maybe I can just go back to that. That's a ways, but... Okay, now here's one of them that I'd like you to add a little bit to. What I had was right, but maybe there's a more complete way to treat this that will help it. So delta T naught is the proper time interval. The naught always means that 0 always means naught, and it always means proper. It's the time between two events as measured by an observer at rest in relation to them, and who views them to happen at the same place. We're still going to have trouble about defining what those two events are, but as far as the viewer, the delta T naught viewer goes, that place doesn't change. Now here's another thing that I want you to think about and add to this. It's also measured by the observer who accelerated. You wouldn't be able to tell who was moving at a constant velocity and who was at rest, because all you can tell is the velocity between two things, but you can feel acceleration. So if you're considering a spaceship or something like that, consider delta T naught, the proper time is measured by the person who accelerated. And that's going to be the person in the ship. We're also sort of looking at we're not so much looking at the time, looking at a clock in between these two events, how that would affect things. We're really only looking at the total time elapsed between event A and event B. Your book has similar to this, but then it's also got some examples that are worth reading. Now, just as a non-judgmental show of hands, who has read the section on time dilation? You will all be judged! So in that section, it's got this. But it's also got some very good examples to go over, including one that is very much like one of the first examples we did. This one is a trip to Alpha Centauri, the nearest star system. Well, Proxima Centauri. Alpha Centauri is one of the stars in the Centauri system. And it says, it explains the same sort of thing, but then it's also got reasoning, and it walks you through, here's why we would do it this way. And seeing different points of view like that can be really, really helpful. So the reasoning for the astronaut being able to measure the delta T naught is this. The two events in this problem are the departure from Earth and the arrival at Alpha Centauri. At departure, Earth is just outside the spaceship. Upon arrival at the destination, Alpha Centauri is just outside the spaceship. Therefore, relative to the passengers on that spaceship, the two events occur at the same place, namely, just outside the spaceship. So if you're measuring the time for that, you would measure the proper time because you are at those two endpoints. The proper time is measured by the person who views them occurring at the same place. Now that's a little bit of a stretch to say at the same place. But if you consider it from an Earth person's point of view, they're nowhere near each other. In this case, they're 4.3 light years apart. In our example at Sirius, it was maybe even a little bit farther apart. Then the other way that can help you is consider the Earth observer or the spaceship observer who would have accelerated during that trip. Obviously, this one on the spaceship would have accelerated. So if we use this, that can really help us figure out which one's going to measure the proper time. Dilated time is always the larger one as well. So the way I typically remember it is by thinking of remembering that the person on in the ship is always going to h less. And so that helps me remember that that person would measure delta t naught because I know it's always going to be less. And so very often that's the way I look at it. But I think those two things can help quite a bit. Delta L, to me, is always, or the length contraction is always easier for me because we observe it readily either way. A person moving quickly by the planet makes it seem squished, makes the planet squished, and also a person from Earth would see a squished rocket. That, by the way, is on the next page, with length contraction in the book, and it's nicely illustrated there as well. So this can be a big help, which is why I have the suggested reading with each of the problem sets, to help you firm up those ideas by seeing them in someone else's words other than mine. Mm-hmm.
So delta t is the person whose time is moving slower or faster?
Faster, they would experience more time. Delta t is always bigger than delta t naught. So a person who measures a delta t naught on the spaceship might only measure a year. And the person on Earth would be 10 years, for example. Mm-hmm.
So the person who... So the person who's experiencing slower time is the one who's accelerating?
Correct.
Okay.
Yep. Any other questions? I know it's still not easy. Don't get me wrong. But with practice, we'll get there. Let's talk about something that makes perfect sense then.
Not math.
And that is the how things get more massive when they move fast. Makes perfect sense. That's a joke. You can smile hypothetical time. Okay. We've got an alien vessel zipping past a deep space station at 0.85 C. Instruments on board the station measure its length to be 123 meters and its mass to be 13,500 kilograms. The vessel later docks at the station. What would the station instruments now measure its length and mass to be? So let's look at length first. The space station measured its length. Is that L or L naught? Is it the proper length or the contracted length?
Contracted.
Why? How do you know?
Because it was accelerating.
Don't worry about acceleration right now, but it was moving in relation to the space station. So the space station won't be able to measure the proper length until it's at rest next to it. So this, I gotta start this up. That length given is our L, not the proper length. It's the contracted length. Okay, its mass was measured as it zipped past to be 13,500 kilograms. Don't ask me how they measure it. How, or which would that be? Would that be M or M naught?
I'm not.
How do you know?
I just take the one that makes sense to me and do the opposite.
So why did the other one make more sense to you?
Because I always think that when they're observing from a different place, it's M naught, or M. So then I just take the opposite of that, which would be M naught. Stop confusing me. The opposite.
All of these, the proper measurement is always made when you're at rest relative to the thing.
So the M.
This is M, because, so you were right in your first inclination. When something is moving relative to you, you're going to measure the improper. If it's at rest compared to you, if you could put it on a scale and have it sit there, then you'd measure the proper one. This is measured by the space station as the ship is zipping past, so it would be the relativistic mass. Mm-hmm.
So something I'm confused about is there's L, which is the improper length.
Yep, contracted length or relativistic
And
length.
then there's M, which is the opposite with the mass. So the M0 would be the proper one.
All of the naught, that zero always means proper.
So L0 would be the proper one as well?
Yep.
What
proper. Typically speaking, what you're going to see is that 0 can be made when you're traveling with the thing. So if you're in the ship, you could make that measurement. If you are looking at something that is moving relative to you, you can't make that the proper measurement anymore. So we've got an L here. We want to find an L naught. We said that rearranging our formula, 1 minus v squared over c squared. And then we also have an m there, and we want to find the m naught. But rearranging our equation from yesterday, m naught is equal to m times our radical. Pretty sure I got that. Yeah. Okay, let's put our values in that we already decided on. 123 meters for the relativistic or contracted length. I'm not going to write the c in here because I know the c's are going to cancel. So I get the 0.85 squared. Instruments on board the station measure its length. So what we are actually finding now is later on when it's docked, or even if you were on that alien vessel, what would you measure the length to be? That's what L naught is. Because the aliens on board are at rest relative to their ship. They see other things moving. Are we moving right now? A lot. We're moving very, very quickly through space on Earth, but we aren't moving relative to the things right around us. And so that means we could make all of these proper measurements because the table isn't moving relative to us. It is moving relative to the sun or the moon or Mars or anything else outside of Earth, but it's not moving relative to us. So we can make these measurements on the things around us. Same thing would be true if we were on a very, very fast-moving spaceship. All the things right around us are moving at the same speed. So in effect, they're not moving compared to us at all.
So if the thing I'm measuring is, if I'm not moving relative to the thing I want to measure, that's not...
That is the proper version.
Yeah,
Yep.
That's like L naught, delta T naught.
Right. Yep. I just want to make sure, because that's not N-A-U-G-H-T. Yeah. Yes, Skylar.
So in this case, L naught is bigger than L?
Is it?
Yeah. Because when you divide by a fraction, you get bigger numbers.
So what you're saying is when things go faster, they get shorter.
Yeah.
Sure.
That's consistent with what we've been saying.
Okay, just making sure
Yep.
L naught.
Yep. L naught's always going to be bigger than L because when something's moving, it shortens. You'll always get the same result. If you get something else, then either you're thinking about it funny or you've done something funny. You got it?
230 meters. With significant. No. Not with the decimal. It would be 233, but since
Thank
it's
you.
0.85.
230. Yep, no decimal. I can't erase it though.
Yeah, try to figure it
Yep.
Makes it
So-
too suffix.
I feel like they should both be the right times because it's just on board the station I'm measuring, are instruments compared to like relative to the station at rest.
But it's measuring the thing on the ship that's going past it.
There aren't instruments on board the station.
Yes, but the station is here, and the ship is going like that. Right? So the station is measuring the ship.
Yeah, I'm not
and they are moving relative to each other. I think you're just confusing with the terminology of it. Yes, ma'am.
So when you say that, that means that wouldn't the person sitting on the couch watching the baseball game on TV, wouldn't that be not?
That can be proper because that person is not moving their position, and neither is home plate relative to each other. Right? They're always going to be the exact same distance apart. Yes?
We have to memorize equations.
Never have yet. I always put them on the hard part is always knowing how to use them. And that's particularly hard in this. The math isn't too bad, but
So not is pretty much if there's a ship, it's on the ship.
yes.
Yes.
And the other one's grounded.
And the other one
Don't
is
always go
not-
there. We'll talk about that after we're finished with this, because if you're making the observation in if the ship is making the observation on the state about the station would be more massive. It would be shorter,
Yeah, whatever you're trying to do.
because your measurement devices are not with staying still. So let's do the next one too. We've got 13,500 kilograms. You can't. The lesson is you can't measure accurately if you're moving compared to that other thing, or at least your measurements are relativistic, and you have to.
L is because we're at the 123 is L because we're at rest.
Because the station is at rest. It's not really at rest, but they're moving relative.
According to
Sure.
relative to the alien vessel, it's at rest.
Right. I mean, they're moving. The real thing, that relativity, that whole thing about relativity is that you can't say one thing is at rest, ever. Only that if it's moving relative to something else. Now, everything in one frame of reference works normally in physics. Like on Earth, we are moving, spinning and things, and that causes some acceleration, but not enough to really make a big difference. Or in a spaceship, you could do, assuming you have gravity, you could do any of this normal measurements that we would do on Earth. It's only when you're trying to make a measurement from one reference frame into another one that's moving that we have trouble. But otherwise, the physics works perfectly normally from what we saw earlier this year. Yes?
So whenever you're moving the same with the object you're measuring,
Then you're okay. Then your normal measurement. Yep.
Then you have the M naught, L naught.
Right. Those are the so-called normal measurements. Okay, we would find the mass to be 7,100 kilograms. So a lot less massive once it slows down as well. Yes.
So you told me that relativity means like compared to earlier. What does relativity mean?
Relativity means that physics works for you in your own reference frame, but whenever you are moving relative to something else, we have to take this into account.
So what does relative to something else mean? Is that like
That you're changing, you're not the same distance apart in the same direction from time A to time B.
So it's like Earth and measuring the spaceship.
Yeah. Yep. So those two are moving at different. Now Earth relative to us, we're moving at the same rate, so we can measure things here on Earth. No problem. But once something else starts moving, now, yeah, we already talked about that. Okay, it's going to take practice, and that's okay.
Yes, we are. Physics Illustrated is going to be fun.
I know. Yes, got it.
So momentum can never change even if I go like that?
The overall momentum can't, because while the momentum of this is increasing in that direction, something else has to increase the same amount in the other direction. So that could be you. It could, if you're solid on the ground, it could be the whole Earth gains momentum that way. It just wouldn't notice because that's really tiny.
But when I move this thing, What, does momentum change when I'm moving it?
Only while it has a different velocity, yes. But when it slows down, it equalizes back the other
So
way.
when I move, it doesn't change its mass at all?
No.
Okay.
Such a small bit. So that's a good question. You know, what happens to the mass and stuff when you move your book or when you throw a ball? Does this happen? Absolutely. But let's look at these speeds. Everything's multiplied by this equation, or this 1 minus v squared over c squared under the radical. But let's just say that you are a really fast pitcher and you can throw a ball at 100 miles per hour. That is going to be, how fast is that in meters per second? Let's just call it 100 meters per second. 30 meters per second. So it wouldn't even be that much, probably about 50 meters per second then. Let's just figure out what that radical is with something thrown 50 meters per second. So our v squared would be 50 meters per second. And we'll square it. Down on the bottom, we have 3 times 10 to the 8 meters per second for the speed of light, and we're squaring that.
It's like 44.7. What?
What is this? This is not 44.7.
No, the 50 is actually 44.7.
Okay. My point will be, if I put this in my calculator, I doubt that it can even it can't even display how small of a difference this is from 1. It's 1 with a whole bunch of zeros. Which means this is actually affecting us all the time. Every single thing that's moving is affected by this, but by such a small amount that all our physics works normally. So Newton was right. Perfectly right. Well, not perfectly. He didn't know about this, but for all intents and purposes, we can't even measure this at most normal speeds. We have done some experiments with very, very precise clocks traveling on fast jets, airplanes, that we've been able to measure it around Earth. We have used it for astronauts in space who are moving very quickly. But even with them, the difference is very, very small. And for anything normal in our lives, cars, even planes, this is an unmeasurable amount. So we don't see it. It is there.
So
We just don't have to worry about it.
Increasing or decreasing its mass? It's increasing?
We would be you run, you increase your mass slightly. Yep. Yeah, you might seem like it. If you jump out of a building after physics class, you will get heavier as you fall. For a couple of reasons. One, you're closer to the center of the Earth, but also because you're moving faster and faster until you are not anymore.
Okay, so back when Einstein was theorizing about all
Yep.
this stuff, they obviously didn't have airplanes or things that
Correct.
flew or anything. So what was he considering?
Let's see what he was considering.
Trains!
That for the,
One of his most famous, thanks for the lead-in, his most famous that everyone will recognize when we're done. Consider a photon. Photon's that little particle of light. Maxwell's equations gave it momentum, but no mass. Said it was massless, but still had momentum. How can this be? Let's find out. Einstein realized that the energy of the photon must be equivalent to some quantity of mass. We can actually even show that photons must have momentum very easily in our own labs. Radiometer, it's called.
I like radios.
And look how interested these children on the package are. Oh, and we didn't even see this kid. Well, same kid, but look how enthralled he is.
I think we can be.
Then he finally gets to physics class.
Then his will is crushed.
He died later that day.
An operable brain tumor. It made him excited about everything.
We just went from happiness to death.
Okay, so this is our radiometer. It is an evacuated globe, so it's a vacuum in there. It's got a pin sticking up, and then balanced on that pin, you can see the white, or the four squares. One side is painted white, one side is painted black. Say, if I threw a ball against a wall made out of either cement or mud, and the collision takes the same amount of time, but the ball bounces straight back from the cement wall and sticks to the mud wall, which, if either, involves more force? Several of you corrected this on your test. Yeah? Right. Because momentum is a vector. It was going this way, now it's going that way. That's a 2 times the momentum change of the ball that hits and sticks, which just goes to 0 momentum. Okay? Let's think about that as we are looking here. We've got a mud wall, and we've got a cement wall.
If they were both the same color.
I'm actually surprised. I expected it to go the other way. I forgot why it was like this way.
So the black is like the mud, and the white is like the...
Other way around.
No.
That's what I expected. But the black is it's absorbing. Oh, that's yeah.
That's why.
Even yeah, but if it were going the other,
Well,
if it's reflecting, but the white reflects in all directions. If it were mirrored, we might see it differently.
See the kids like this so much.
I know. Isn't this awesome? A brighter light would make it go a little faster. Maybe I can.
Let's bring that flash.
Now I can see it.
And it'll continue to go faster a bit. It doesn't have drag in there because there's no air.
So there are so many photons hitting that's moving.
Uh-huh. Which proves
If you
almost
try-
beyond a doubt that these have momentum. Not necessarily mass. Yeah.
So if you got a really, really bright light and shined it at me, could it knock me over?
Yes.
Cool.
Yes,
Blindness.
Then burn you.
You told me that momentum is mass times velocity.
And how can something without mass have a momentum?
Boom.
First question, and second question, what is momentum then? I mean, how could you explain momentum without math?
Without math. We had that as our last one, which we've got our colors. Momentum is sort of it's not really a force, but you can think of it as the inertia. Are you familiar with that word? That's not a common English word. It's sort of the force behind something that's moving. How much oomph it has, we might say. Yep.
What is a photon?
A photon is a tiny particle or a packet of energy that is transferred by electromagnetic radiation, like light or X-rays or radio waves.
So it's not an actual object.
It is not an object. But it does have, like everything else, it does have properties of both waves and particles.
So in this case, something multiplied by 0 does not equal 0.
Well, and yeah, let's look at our last mass equation though. So a photon, it says, has no mass, but we said yesterday that the relativistic mass is equal to the rest mass over 1 minus v squared over c squared. Well, a photon has 0 mass. If this is the speed of light, the velocity at which a photon travels, that's c, right? What's c squared divided by c squared? What's 1 minus 1?
0.
What's 0 divided by 0?
0.
No, it's apparently something.
It's infinity.
No, it's not infinity either.
What did you
Math would say it's undefined.
1.
There's no answer.
It would be 1.
It's something.
But it's also 2.
But it's undefined.
It's undefined. But that doesn't, in this case, necessarily mean nothing if we extend this to it. Now, nothing with mass can go this speed. We'll discuss why after we get through this. But let's see if we can get through this one today. I think we can. Here's Einstein's thought experiment, another great experiment that at least allows you conceptually to understand where he's coming from with this. We have a stationary box and a frictionless surface. I believe he said a train car, because he dug train cars. There is a photon emitted from inside the box, traveling parallel to the surface. So going from one side of the box to the other. It's absorbed when it hits the other side of the box. All right? So we got a box here, actually here. And a photon will be emitted from this side, go across to the other side of the box, and be absorbed. And this is a frictionless surface. Again, he did it with a train car. I think I got it. See? Look at that photon.
It's so majestic.
I know.
It's like a goose. YouTube is lagging.
Oh, okay, so let's continue on then. What will this mean for us?
More confusion?
A goose? I think you just got to get closer. You can, up here you can see the wave.
You can, from here too, it still looks like a goose. Use your imagination.
It's a goose named Bolero.
I think you're all mad. I can see it now because it looks like the black head of a Canadian goose.
His name is Photon.
It's Photon the Canadian.
Bang!
Okay, from Maxwell's equations, which Einstein based his work on, which seem to be working perfectly well, you can show that the momentum, which is a p of a photon, equals the energy of the photon divided by its speed, c. We're not going to worry about how that comes out of Maxwell's equation. Okay, that's a momentum. So this should cause the box, if the momentum is that way from the photon, it should cause the box to recoil. Just like if you are in a very low friction chair and you throw a ball, you go backwards. Same thing, except this is much, much lighter. But it should recoil a tiny bit. Now, when this thing strikes the box on the other side, it should stop. Right? Because now that momentum that the photon had hits the other box. The same thing would occur if you and a friend are sitting on a very low friction cart. You throw a bowling ball at your friend, who catches it and collapses, but stays on the cart. You would move while that bowling ball is in the air, but as soon as your friend caught it, you'd stop. Because now this momentum is going back into the box. And so, although it might have been sliding that way, now it just got to push the other direction. So it'd stop again. But here's the problem. The center of mass of that box, which used to be right here, since the box moved that way, is now to the left. So, there were no outside forces. This was completely interior, but the box moved, and as we learned, that's only possible if the center of the mass of the system didn't move, which means that in order for this to work, our bowling ball can switch sides. We have no problem with that. And the cart can move a little bit, but if we took the center of mass, it would have to be at the same side when we averaged all of that. It'd have to be right at the same location, which means that can't happen. The photon must have some sort of equivalent mass. Even better.
What?
Okay, so now we're going to apply the law of conservation of momentum to this. The momentum of the box here We know what that would be. That would be its big mass times whatever velocity it got as it was moving. We can also say that this v, this velocity, would be how much it changed in x divided by how long it took. And because of that conservation of momentum, we know that it has to be equal to this. The photon must have the same momentum in that direction that the box had in the opposite direction. So that would be our E over C. Okay, so now it's a vector, so one would be positive, one would be negative. We're ignoring that for now. We're just looking at the magnitudes of these two. We can also say that the time that it took here, the delta t, well, how long would it take a photon to go from here to there? It would be the length of the box divided by the speed that it went. So length of the box divided by the speed of the photon is c. Okay, so I'll put that up here, the L over c, up for my delta t, but then I'm also going to multiply that across. Yep, multiply that across. So what I get here then is that this, I don't want to do that. I'm going to do it on the board so I can.
Why would you multiply it across?
Because I want to. Because I know where I'm going.
I don't.
Yeah.
They have an equal time.
Yep, I'm going to write it out up here so we can all see it really clearly, what I'm doing. So I'm going to start my m times delta x, and I'm going to put my new value, the L over c, up there. That's an L, not a 4. And that's equal to what I have here, the E divided by c. And then I'm going to multiply both sides by 1 over this, so effectively the c over L to cancel this out. No, sorry. I'm going to multiply by L over c. So that would leave a delta x here, but it would make an L over c from here times EC. Or in other words, gathering those like terms, we'd have an E times an L on top over a c squared on the bottom. What's that? The big M is the mass of our box. The L is the length of the box. The E and the C, the E is the energy of our photon.
So we're trying to solve for what again?
You're going to see. Again, we're not trying, I know where we're going. We're trying to simplify this, though, now, and make it into something that we can actually use. And you will be stunned when you notice what it is, when you figure out what it is. Then hold your tongue and let everyone enjoy the moment.
I think I see it
Okay,
already.
now let's look at this. Now the center of mass for the system has to stay in the same place. Before the collision, we would have the center of mass, so the mass of our box, it would have a center of, let's just call it x1. That's just its starting point. And then we'd have a mass of the photon, and it would have a starting position of x2. That's on the side of the left-hand side of the box. And then to find center of mass, we divide that by the total mass. We haven't really done that here, so just trust me on that one. Okay, so that's before. But now this can't move, right? The bowling ball thing. If I throw the bowling ball to the other side, the cart moves, but that's offset by the mass of the bowling ball movement. So that's got to be equal to where it is afterwards. And that we could describe as we're gonna move our starting position of our main mass by just a little tiny bit. We're going to call it delta x. Okay, and the photon, well, that moved all the way across the box. So it went to position L. And again, that's divided by the sum of the masses.
So ML equals what on before?
Sorry?
ML equals what on before?
The length of the... M is the mass of our photon that we're trying to work on. L is the length of our box, is how far it traveled, essentially. Now, we're going to simplify this a little by saying that the edge where this started, we're going to call that 0. Just like we did with a lot of other problems, we can usually define one position as 0 and just measure everything else compared to that. Okay. Now the m plus m, obviously that's the same on both. So those two are equal. So the tops must be equal, right? So this top on the left, could we not see it?
Not all of it.
The left-hand side, all that's left is our mx1, because I canceled these out. And that would have to be equal to what's on our right. M, and just distributing the x, mx1, same as there, minus big M times delta x, plus little m times L. So, mx1 and mx1 cancel. So that must mean these two terms are equal in order for this now to be equal to 0. So that implies that the big mass of the box times the little bit it moved must be equal to the little mass of the photon times the length of the box, the distance it moved. Oh, we are so close. Oh, deliciously close. Delicious. I'm going to take this here, and look, we saw that term before. I'm going to put my value of this ML right up there.
Wait,
Okay,
you're replacing it?
I'm replacing it. I'm replacing, so this term now becomes little m times L. Length of the box. And that's still equal to this thing on the other side. E times L over C squared. Well, L's cancel. I'm going to multiply both sides by this square, C
Oh,
squared.
you're kidding me. I'm done. Okay. Physics is
The
done
most
today.
famous equation ever.
What is the E again?
E is the energy.
Oh, the photon?
What Einstein proved by doing this, I did. What Einstein proved by doing this is that there is an energy equivalent to mass, to anything with mass. And also, based on this thought experiment, that photons, even though they don't have, they can't be at rest, you can't measure their mass, they have energy,
Yeah.
and therefore they have an equivalent mass as well.
We just don't know it yet.
No, we can measure it. In chemistry you learn how to measure the energy of photons given off by things. That had actually been known for a while because of people named Planck and Heisenberg. No, Planck is later, maybe. Heisenberg's much later. Mm-hmm.
So, to find the mass, you take the energy divided by C squared.
We got a couple minutes left. So, go ahead.
To find the mass, you take the energy divided by C squared.
And so we're gonna do this. This took a while to get proved, about 40 years. A woman named Lisa Meitner, who was Jewish and fled Germany, went to Norway. She was one of the most instrumental in figuring this out because they were also starting to learn about nuclear fission, where atoms break apart. Well, as it turns out, those atoms, the remnants after a big atom breaks apart, are slightly less massive than what it started with. And they were very, very interested in, well, we must be measuring something wrong because the mass went away. Those particles gained energy, and so she was the first person to show that that energy that the particles gained in fission was exactly equal to this, and that proved this portion of Einstein's theory.
This before or after?
This was before he died. It was still during the war. So this is, we kind of use this to make the first nuclear bonds and fission and all that. Okay, that's it for today. You can begin working on the next homework now. Tomorrow, what do we have?
Physics Illustrated Word.
Yep, a couple practice problems, and we got to work out time on. Yep.
Yep, my head's exploding.
Good stuff.
It's like as soon as you got to the C squared, it's like